Welcome. In this session, we'll talk about transfer function of a network. So let's suppose we have a network, a system. Where the transformer input is X and transformer output is Y. So transfer function of a system is simply defined as, so TF, short for transfer function, is simply defined as Y divided by X, where X and Y are transformer input and outputs. Okay, so what I mean by transformer input and output means Laplace transform, Z transform, or Fourier transform of input and output. So Laplace transform, Z, or Fourier transform versions of the input and output. So if I take the output Laplace transform output and divide it with the Laplace transform input, that is referred as the transfer function of the system. For example, I say our network or system where X of S is the input and Y of S the output, then transfer function of this network or system will be simply Y of S divided by X of S. Okay, very simple. So output transform divided by input transform is referred as the transfer function of a system or network. Now in this session, what we'll do, we'll learn how do we obtain the transfer function of a network first. And second, if we know the transfer function of a network, how do we determine the output of that system? Okay, so let's start with a basic simple network. Let's start with an example. Let's suppose we have a very simple RC circuit. Connected to a voltage source. Input like Vi of t. Resistances R and capacitor values C. Okay, and our output in this network is across this capacitor. Our output is this. Okay, so in order to obtain the transfer function of this network, what the first thing we do is we convert this network in the transfer domain. For example, the transform domain here means simply either we convert it into the Laplace transform domain or Fourier transform. Now, Fourier domain is also referred as phasor domain that we already saw in the previous sessions. Okay, so let's convert it into the Fourier transform domain. Yeah, sorry, Laplace transform. Okay, so let's draw the Laplace transform version of this network. What happens to R in Laplace transform? Resistance is simply replaced by R. What happens to a capacitor in Laplace transform domain? If the initial condition is 0, then the capacitor is replaced by 1 by S. C, that's referred as the impedance of this network. Then input Vi of t will be called Vi of S, as we don't know what's Vi of t, so we'll write it as Vi of S. Similarly, we'll say V naught of t will denote as V naught of S. Okay. All right. So how do we obtain the voltage V naught of S in this network now? Right. So if you look at this network, we have two impedances, R and 1 by SC, connected in series with the voltage source. So if we apply a voltage division rule here, we can use any circuit analysis technique to find V naught of S. But let's start with the voltage division rule. So if we apply voltage division rule in this network, so V naught of S, which is the voltage across the impedance 1 by SC, will be simply given by V naught of S will be simply the impedance of the element divided by the total impedance. Total impedance is 1 R plus 1 by SC multiplied by the source voltage. Okay. So if we simplify this equation, you get V naught of S 1 by SC will in the denominator. So we'll write it 1 plus R CS multiplied by V naught of S. Let's divide both sides by VI of S. So dividing both sides by VI of S, so V naught of S divided by VI of S is simply equal to 1 divided by 1 plus RC S. So the transfer function of this network is simply this. Output transform divided by input transform is referred as the transfer function of this network. So the transfer function of RC circuit is simply 1 divided by 1 by RCS. We can also write it if we take RC common from the denominator. We can write this transfer function also as V naught of S divided by VI of S. We take 1 by RC common. We will write it 1 by RC S plus 1 by RC. We can also write this equation as like this. Okay, so the transfer function, which is usually denoted by the letter h of s, a function what h of s is equal to this. So this is how we obtain the transfer function of a network. Okay, we relate the input with the output by using the network analysis techniques, different network analysis techniques. Similarly, suppose same circuit, only difference is the output is not the V naught of T, output is the current flowing in the circuit. So if the current is the output now, okay, in the previous case, V naught of T was out. Now our output is now I of T. So how do you obtain the transfer function in this case? Okay, so what we'll do, we'll write it as I of S, and we'll form the equation between I of S, relationship between I of S and input voltage. Okay, so how we relate the I of S with this I of S? If we use simply KVL in this network, we'll get a relationship between the input and the output. So if I redraw this network here, this is VI of S R 1 by SC, and now the output is I of S in transform domain. So if I have to relate I of S with the input, so if I apply KVL, I apply KVL in this circuit. So I start with this point. So it will be minus VI of S, the volt drop in source, plus R, that is the impedance, multiplied by current, is the voltage drop in resistor R. Similarly, 1 by SC is the impedance offered by capacitor multiplied by the current is the voltage drop in the capacitor. It's equal to 0. As there are 3 elements, sum of 3 branch voltages equal to 0 is the statement of KVL. So if we simplify this equation, so I get taking this on the right hand side, it will be R plus 1 by SC multiplied by I of S equal to VI of S. So if I divide, if I take this R plus 1 by SC on the right hand side, get I of S is simply VI of S divided by R plus 1 by SC. simplifying this, dividing both sides first by the vi of s. So I of s divided by vi of s is simply equal to r plus 1 by sc. So output is I of s, input is vi of s. So the transfer function of this network is simply h of s equal r plus 1 by sc. So this is the transfer function of this network. We can also simplify this. This is the transfer function. If the output is current now, if the output is voltage, this is the transfer function. Okay, if the output is voltage, then this is the transfer function, or this is the transfer. Okay? Depends upon transfer function will change accordingly if the output changes or the input changes. Okay, we can simplify this expression here. We can write it h of s. We take sc on the numerator side, it will be sc divided by 1 plus rcs is the transfer function of this network. Okay, so this is the transfer function of this network. All right, so this is how we obtain the transfer function of a network. Very simple. Similarly, in phasor domain, we write output phasor divided by input phasor is the transfer function of the network. Okay, output phasor divided by input phasor is the transfer function of a network in phasor domain. So if I have to write the transfer function in phasor domain or Fourier transform domain, phasor domain is also referred as Fourier transform domain. So transfer function will be simply equal to output phasor depending upon voltage or current divided by input phasor is the transfer function in phasor domain. Okay. Now, once we obtain the transfer function of a network, or if the transfer function is already given to you in system or in any network, how do we obtain the output of that system? Okay, so if I draw a system, or if I have a network, if I draw a network on a system, and x of s is the input in frequency domain, and y of s is the output, and h of s is the transfer function of this network. If h of s and input is given, how do we obtain the output? Similarly, if output and transfer function is given, how do we obtain the input? Okay, we can also do that sometimes, but let's proceed with if the input and transfer function is given. How do you obtain the? What is the definition of the transfer function? Transfer function h of s is simply given as y of s divided by x of s. So what will be y of s equal? That is the output in transform domain is h of s multiplied by x of s. Right. So how do we obtain the output of a system or network in transfer domain? We multiply the input with the transfer function. That's how we obtain the output in transfer domain. Transfer function multiplied by input is the output of a system. Right? So input multiplied by transfer function is the output. But in time domain, what we have to do? We have to convolve the input with the impulse response of the system. Okay, that's the advantage of using Laplace transform or Fourier transform or phasor domain. In phasor domain or Laplace domain, output is simply equal to input multiplied by transfer function. In time domain, output is obtained by convolving the input with the impulse response of the system. Very, very important. Okay, this is the advantage of using transform theory in networks or system theory. Okay, so what we'll do, we'll take an example. Sometimes transfer function will be given, or sometimes you may have to first determine the transfer function, then find the output. Okay, let's use this trans. Our goal is to find the output voltage in this RC circuit, where input, that is V I of t, is simply delta t. R is 1 here, C is 1 farad, and output is across this capacitor. So output is across capacitor. What is the behavior of output voltage, or what is simply V naught of t across this capacitor, right? So what we'll do, we'll obtain the transfer function of this network first, then we'll find the output. So we'll draw the transform version of this network. So transform version of this network will be simply, will replace a resistor with the Laplace transform version. Similarly, we'll say V naught of t will replace with V of S. R will replace with that is equal to 1 here. Capacitor will be replaced by 1 by SC. C is 1, so it will be 1 by S. And V naught of t will be replaced by V naught of S. Okay. So what we have in this network, two impedances connected in series with the voltage source. So how do we obtain the output voltage? V naught of S will be simply equal to, if we apply voltage division rule, 1 by S divided by 1 plus 1 by S multiplied by input. So what is V naught of S? If I divide both sides by Vi of S, so simplifying this term, it will be 1 divided by S plus 1. So the transfer function of this network is simply 1 divided by S plus 1. Okay. The transfer function of this network RC circuit is 1 divided by S plus 1, which is same as that we obtained already here. Here, if Rn C is 1, it will be 1 divided by S plus 1. Exactly same as here. We substitute S R equal to 1 and C equal to 1, it will be the one and the same transfer function. Okay, so we have the transfer function now. Once we have the transfer function, how do we obtain the output? We know output is simply V naught of S is simply the transfer function multiplied by input. What is the transfer function here? 1 divided by S plus 1. What is the input? Now input Vi of t is delta t. Now, what is the Vi of S? Vi of what is the Laplace transform of delta t? 1. So if I multiply this by 1, this is the output. So V naught of S is simply 1 divided by S plus 1. Now this is the transform version of the output, but we need V naught of t. Our goal is to find V naught of t. So what we need to do here, we need to apply the inverse Laplace transform. So if we apply inverse Laplace transform step here, so what is the inverse Laplace transform of V naught of S is simply V naught of t is equal. What is the inverse Laplace transform of 1 divided by S plus 1? Inverse Laplace transform of 1 divided by S plus 1 is simply e to the power of minus t u of t. Okay. So this is the output voltage across the capacitor if we apply delta t as input to the network. Okay. So if we apply delta t as input to the network, output is simply using, and this is the transfer function approach. Okay, this is the transfer function. And transfer function approach is very, very important if the input is a sine wave. Okay, if you know the transfer function of a network or system and input is sinusoidal, you can directly write the output. You don't have to solve anything. Yeah, that's the advantage of using transfer domain analysis or Laplace transform. That we shall learn in the next session. But this is very, very important. So in this session, what we learn, what's the transfer function? Now, transfer function is simply defined as output divided by input. And if we know the transfer function of a network, we can determine the output for any given input. Okay, so what we learned today, we learned how to determine the transfer function of networks. Very simple examples. If the output or input changes, your transfer function will obviously change. Like we solved two examples here. Then to determine the output is simply transfer function multiplied by input. And this is very, very important for a signal system class. Very important for a signal system class. And we solved one example, very simple example. This is so we obtain first the transfer function, then we obtain the output. Sometimes transfer function will be given. So you have to multiply the input with it and take the inverse Laplace transform. Okay, very easy, sir. If you know the how to apply Laplace transform in networks and how to apply inverse Laplace transform for given functions. Okay, very, very simple. Okay, let me end this session here. In the next session, we'll learn how do we write the output of a network directly if the input is sinusoidal. Okay, let me end this session here.